In 1918, researcher Edward Mellanby successfully cured rachetic puppies by dosing them with cod liver oil, identifying what he called an accessory factor in the fat. That accessory factor was later isolated and named vitamin D, a nutrient historically defined by its ability to prevent the bone disease rickets. For most mammals, synthesizing this nutrient is straightforward. Ultraviolet B radiation, between 290 and 320 nanometers, penetrates the epidermis and photolyzes a compound called 7-dihydrocholesterol, or 7-DHC, to produce the vitamin. This diagram compares skin synthesis in humans and dogs. While human skin readily converts UVB into vitamin D, canine skin lacks sufficient 7-DHC. The UV rays hit the dog's coat and skin, but the chemical reaction simply doesn't happen. Unlike sheep, horses, or rats, dogs exhibit almost zero UV-mediated conversion. Their unique biology leaves them entirely dependent on dietary intake. Because this cutaneous synthesis pathway is non-functional, canine vitamin D does not act as a standard vitamin they can synthesize on the go. It operates strictly as an obligate dietary hormone. Dogs must acquire this hormone through two primary dietary forms: cholecalciferol, or D3, derived from animal sources, and ergocalciferol, D2, which comes from plants. While species like cats struggle to process the plant-based form efficiently, dogs possess the unique metabolic machinery to utilize both D2 and D3 with equal efficiency. Modern veterinary medicine now recognizes vitamin D as a powerful steroid hormone that actively binds to receptors in cardiac muscle and immune tissues. This makes the rising trend of unfortified homemade diets a critical clinical concern. These meals rarely contain the baseline concentrations necessary to maintain the hormone's activity across those varied receptor sites. When this dietary intake fails, the resulting deficiency impacts systems far beyond the skeleton, essentially removing a primary regulator from the dog's internal environment. This metabolic map traces ingested vitamin D as binding proteins transport it from the digestive tract directly into the liver. Inside the liver, the enzyme 25-hydroxylase converts the raw molecule into 25-hydroxyvitamin D, also known as calcidiol. Because calcidiol has a relatively long half-life of 10 to 21 days, it remains the most stable metabolite in the process, serving as the definitive biomarker for testing a dog's clinical status. To achieve true clinical sufficiency in dogs, serum levels must hit a target range of 100 to 120 nanograms per milliliter. The risk of toxicity is low within this optimal window, typically presenting only when serum's concentrations spike above 150 nanograms per milliliter. Hitting that 100 nanogram baseline is difficult. A study by Young and Backus demonstrated that supplementing dogs at 5 times the National Research Council's recommended allowance was still insufficient for some dogs to reach the target range. Hitting standard dietary minimums only ensures a dog avoids rickets. Regular serum monitoring is the only way to confirm they have achieved full hormonal sufficiency. From the liver, the flowchart follows calcidiol as it travels to the kidneys for the final stage of metabolic activation. Here, the enzyme 1-alpha-hydroxylase converts the calcidiol into the highly active metabolite 1,25-dihydroxyvitamin D, known as calcitriol. Calcitriol has a fleeting half-life of only 4 to 6 hours, but it possesses the potent ability to actively modulate cell growth and neuromuscular function. While the kidneys generate the bulk of this active hormone, other tissues that express 1-alpha-hydroxylase can also perform this conversion locally to meet immediate cellular demands. Once synthesized, active calcitriol circulates systemically, docking directly into target receptors in distant organs like the heart and the gastrointestinal tract. The systemic reach of calcitriol dictates that its dietary precursor is a non-negotiable component of canine biology, rather than an optional supplement. This map connects calcitriol to its 3 major organ targets. Starting with bone health, when dogs eat unbalanced, meat-only diets deficient in vitamin D, they rarely get traditional rickets. Instead, nutritional hyperparathyroidism leads to fibrous osteodystrophy. The second major target is the heart. Cardiac myocytes rely heavily on vitamin D receptors to regulate essential calcium-binding proteins. Clinical data tracks exactly with this biology. Low calcidiol levels correlate directly with poor outcomes in dogs suffering from congestive heart failure and chronic valvular heart disease, with levels dropping progressively from stage B2 through stage D. The third major target covers the immune system and the gut, where hormonal deficiency is strongly linked to chronic enteropathy. In dogs diagnosed with protein-losing enteropathy, low serum vitamin D is a prognostic marker, significantly associated with decreased survival times. The clinical picture worsens as levels drop. Dropping below the critical threshold of 40 nanograms per milliliter is significantly associated with an increased relative risk of developing cancer. A dog can present with perfectly normal bone structure while harboring a subclinical deficiency that slowly degrades their cardiac and immune function over time. This highlights the immense risk of traditional canine nutrition in regions like India, where homemade diets lean heavily on rice, chapati, and milk. Grains and standard dairy are indigent sources of vitamin D, providing negligible amounts of the necessary hormone. Even cow's milk produced in the summer is only marginally richer than winter milk, still falling far short of a dog's metabolic requirements. This chart compares the nearly untraceable vitamin D levels in a standard rice and grain diet against the Association of American Feed Control Officials maintenance minimum of 500 international units per kilogram of food. Without deliberate, calculated supplementation, the vast majority of dogs living on unfortified homemade diets exist in a continuous state of undiagnosed hormonal insufficiency. Bridging this gap requires highly specific, nutrient-dense additions. Boiled egg yolk serves as a highly accessible and financially feasible starting point for these households. A standard 17-gram chicken egg yolk yields approximately 37.1 international units of vitamin D. For a significantly higher yield, specific regional fish species, such as Amblypharyngodon mola and Puntia sophore, provide exceptional natural concentrations. The mola carplet, for example, provides over 90,000 international units per 100 grams of wet weight. When dietary adjustments are impractical, exact clinical dosing can be achieved using commercial supplements like cod liver oil or targeted veterinary tablets and syrups such as Nutricheck. Veterinary medicine must prioritize educating owners that vitamin D functions as a life-extending hormone, one that requires active management through targeted clinical nutrition.